Okay, imagine this. Out there in space, there's this object. Astronomers are actually calling it a cosmic unicorn. It's completely baffling. We're talking about a dead star. But here's the kicker. It's not just spinning, it's somehow speeding up.
Yeah, that's the part that flies in the face of everything we thought we understood.
Right. It just completely upends our ideas about how stars, live and die. So today, we're doing a deep dive into the latest research on this thing. Its official name is CHIME J1634+44.
Quite a mouthful. Cosmic unicorn is catchier.
Definitely. We'll explore why it's such a deep mystery, what it could mean for our whole picture of the universe.
Yeah.
And we're digging into recent findings from major observatories and research teams here.
And I think it's important to stress, this isn't just, oh, look, something new. This is potentially revolutionary. It's like the universe just threw us this massive curveball that challenges some really fundamental physics.
Right. It forces a rethink.
Exactly. It makes scientists look again at the basics of stars, their death, how they behave afterwards.
Okay, so let's unpack this cosmic unicorn a bit. CHIME J1634+44. It fits into this relatively new category called Long Period Radio Transients, LPTs for short.
A very mysterious group.
Yeah, exactly. So these things, they emit radio bursts, but like over minutes or even hours. That's way, way longer than your typical pulsar, right? Those rapidly spinning neutron stars.
Oh, vastly longer.
Yeah.
Pulsars are usually milliseconds to seconds. We're talking a completely different timescale here.
But even within this weird LPT group, CHIME J1634+44 just stands out. The sources say it's the brightest one ever seen.
By far.
The most polarized, too, and its radio pulses have this strange, almost choreographed feel to them.
A distinct pattern.
And here's the part that just blows my mind. It's the only LPT they've found whose spin is actually speeding up. I mean, when you hear dead star, you think it's winding down, losing energy.
That's the standard picture, yes.
So what's the core physics reason this is so perplexing? Why shouldn't it be speeding up?
Right, you've nailed the central puzzle. It really does challenge the known physics for these stellar remnants. So, quick recap. A massive star dies. Its core collapses into this incredibly dense neutron star.
Okay.
You're taking something maybe 1 or 2 times the mass of our sun and crushing it down to like 12 miles across. It's unbelievably dense. A single teaspoon would weigh 10 million tons.
Wow. That's what, 85,000 blue whales are?
Something like that. Just staggering density. Now, there's this principle, conservation of angular momentum. Think of an ice skater pulling your arms in to spin faster.
Right, yeah.
So when the star collapses, the remnant, this neutron star, starts spinning incredibly fast, maybe 700 times a second for young ones. But, and this is the key, the expectation based on physics is that over time, they lose energy, they radiate it away, interact with their surroundings. They should slow down.
Okay. Like a spinning top losing steam.
Precisely. So for CHAE J1634+44 to be accelerating, speeding up, that's a direct violation of what we expect. It's a genuine puzzle.
That is astonishing. So, boiling it down, what's the sort of single most revolutionary idea this forces astronomers to grapple with?
It's basically that our rule book, our understanding of how these dead stars behave, it's incomplete. There's something missing. This object suggests there are maybe physical processes or perhaps even whole new types of interactions or objects that we just haven't factored into our models yet.
So this cosmic unicorn really does challenge everything we thought we knew about stellar evolution. But scientists aren't just stumped, are they? I mean, there must be some leading ideas, some theories about why it's speeding up.
Oh, absolutely. They're definitely not just shrugging. The frontrunner hypothesis involves a companion, a nearby star locked in orbit with it.
Okay, a binary system.
Exactly. In a really tight binary system, the idea is that these two objects orbiting each other would be so massive and close they'd actually warp space-time around them.
Yeah.
And that warping creates ripples gravitational waves.
Right, pure energy radiating away.
Precisely. And these waves carry away energy and angular momentum from the orbit itself. It's almost like a cosmic drag, causing the two objects to spiral closer and closer together. As they get closer, the orbital period gets shorter, which looks like an acceleration from our perspective.
Oh, okay. So it's the orbit tightening, not necessarily the star itself spinning faster intrinsically.
Well, it's linked. The orbital mechanics are driving the observed spin behavior. And this kind of orbital tightening, this decay, it has been seen before in other binary systems, particularly involving white dwarfs.
Gotcha. So a companion could explain the speed up. That ticks one box, maybe. But I read there are other weird things about this object, too, beyond just the acceleration.
Oh, yes. the spin-up is just the start of the weirdness. The research suggests the companion could be another dead star, a white dwarf, or another neutron star, or maybe even something called a brown dwarf.
A failed star, right.
Essentially, yeah. Something that started forming like a star, but just didn't get massive enough to kickstart nuclear fusion. So, yeah, the nature of this companion is another big question. What kind of cosmic dance partner does it have?
And then there are these other bizarre features the sources mention. First, the radio bursts are apparently 100% circularly polarized. What does that actually mean, and why is it so unusual?
Okay, so 100% circularly polarized. Imagine the light waves, the radio waves, aren't just oscillating up and down or side to side. They're actually spiraling as they travel towards us like a corkscrew.
Huh.
And getting 100% polarization like that is extremely rare. It tells us something really specific about the conditions where the radio waves are being generated, maybe incredibly strong, ordered magnetic fields, or very particular plasma environment.
And the key thing is, it's not seen in other pulsars or white dwarfs.
Never been seen in bursts from either neutron stars or white dwarfs before. That's the crucial point. It strongly suggests the mechanism generating these radio waves is unique, something we haven't encountered. It's a major clue that we're dealing with something fundamentally different here.
Wow, okay. And the other strange thing was this choreographed pattern of the pulses, like they arrive in pairs.
Yeah, it's really peculiar. The bursts seem to come in pairs, but not every time the star spins. It spins multiple times, apparently silently, and then emits a pair of bursts.
So it's not just random flickering?
Not at all. Scientists are actually quite excited about this pattern. They think the specific timing, the gaps, the pairs, it holds vital clues about how the companion star might be triggering the bursts from the dead star. It's like the system is sending us a coded message about their interaction.
That's fascinating. And I understand there's even disagreement about what this dead star actually is. Neutron star or white dwarf?
That's right, which adds another layer of intrigue. One research team crunched the numbers and leans towards it being a neutron star. Another team looked at the data, particularly things like the polarization, and suggests it might be a highly magnetized white dwarf.
Okay, so they don't even agree on the basics.
Well, on the type of remnant. But what's really interesting is that both teams, despite reaching different conclusions about its identity, completely agree on how utterly strange and unique it is. They both basically say, whatever this thing is, we've got a real mystery on our hands.
So this isn't just about one oddball object then. Finding CHIME J1634+44 seems to have wider implications.
Definitely. It, first of all, significantly expands this population of LPTs. Finding more helps us understand the class better, but more profoundly, it directly challenges our existing models for both neutron stars and white dwarfs.
Right, because it doesn't neatly fit the expected behavior of either.
Exactly. It's like, finding a mammal that lays eggs, it forces you to rethink your categories and assumptions.
Yeah, it suggests our textbooks might need a new chapter.
Or at least some significant revisions. And connecting this to the bigger picture, it hints that we might be entering a really exciting phase in radio astronomy. Maybe there are lots more of these cosmic unicorns out there just waiting for our telescopes to get sensitive enough to spot them.
So our understanding of what happens after stars die is still very much a work in progress.
Absolutely. We're likely just scratching the surface, and these advanced new instruments are letting us probe these extreme objects in ways we couldn't before. It suggests we're probably on the verge of some major breakthroughs.
This whole deep dive really underscores how just one set of new observations can shake things up, scientifically speaking. It just makes the universe feel even more mysterious and, frankly, more interesting.
Keeps us humble, doesn't it?
It really does. So we're left thinking about CHIME J1634+44, this dead star, defying the rules, spinning faster, sending out these incredibly specific, polarized, choreographed signals. It just pushes the limits of what we thought was cosmically possible.
And it leaves you wondering, doesn't it? What else is out there? What other objects are quietly sitting in the cosmos, completely defying the physics we think we know, just waiting for the next generation of telescopes to stumble upon them?
Yeah.
And what does it even mean for a star to be dead if it can still surprise us like this, still be so dynamic? It seems the universe always has more secrets, always reminding us that our maps are, well, constantly being updated. There's always more to learn.